Hey everybody, it's Mrs. Mancuso. So we are continuing on learning more about electrons and ionic compounds. So grab your packet. We're going to work through this together. There's going to be parts where you stop and you do more practice problems. And then we're going to end with a lab. So what do we know already? So first of all, in an ionic compound, the metal is going to lose electrons to the nonmetal. We call that transferring. So transferring is another great way of saying it. The number of electrons lost by the metal blank the number of electrons gained. Oh, these always have to be equal. So if you lose 2 electrons, your nonmetal is going to have to gain those 2 electrons. The loss of electrons is known as oxidation. Oxidation always happens at the anode. And to gain electrons is reduction. And that always happens at the cathode. So an, ox, red, cat, those are ways of remembering which ones go together. And if you are losing electrons, you're oxidizing. Think of like a metal. A metal oxidizes. It loses its electrons. We call them left side losers. So you can always think of metals oxidizing. And reduction, if you keep getting more and more negatives, your charge keeps going down, 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 down. So that's why it's called reduction. All right, so that's what we already knew. Now we're going to move on to some new stuff. So scientists after J.J. Thomson studied the arrangement of these tiny negative subatomic particles and found that they tend to occupy specific regions. Okay, we have a lot of names for these areas within an atom. We call them energy levels. Like you can level up, like there's different levels around inside of an atom. Or we call them rings or orbitals or shells. So a lot of names for these, but it's all of that plum pudding area where our electrons are in an atom. The outermost electrons, so the ones which encounter and potentially interact with other atoms, they're called valence electrons. So if this is my atom, the ones that are furthest to the outside, those are the valence. Those are going to be the ones that can come in contact with other atoms. They're going to be super important today. All right, to determine the arrangement of electrons, you simply look at the electron configuration on the periodic table. Where is the electron configuration in the element square? So I want you to go to your periodic table right now, and right up top is the key. And the key shows you atomic mass, the symbol carbon, the atomic number, and then, ooh, there it is. So it is on the bottom left of each square. So every element down here at the very bottom left gives you its electron configuration. Look up potassium and draw its atom with 4 energy levels. The first one listed is the inside. Work your way out, drawing little electrons on the appropriate energy level. So K is potassium. The electron configuration is 2881. So I'm going to put K in the middle, and I'm going to put 2 electrons on my first energy level. Check, did it. 8 on the next. And I spread them out because negatives don't like each other, so I need to give them space. 8 on the next one. Check. And then the last one, the valence electron, is just 1. Okay, of all of potassium's 19 electrons, circle the one that is most likely to be involved in the bonding of this atom. All right, there it is. That one is the outermost electron. So that is the one to be most likely involved in bonding of this atom. Now repeat the drawing for magnesium. So I want you to pause the video and go and do your magnesium drawing. Then I want you to do your argon drawing. And argon is unreactive, so there's nothing to circle. So instead, I want you to start thinking about why it doesn't react. And then I want you to repeat it for oxygen and fluorine. All right, so at this point, you're stopping the video, pausing, and then come back to me when you are done. Okay, so I'm assuming you are done. Stable atoms have a full energy level of valence electrons. Which elements on the periodic table have a full energy level as an atom? So to be full, we are going to notice that they do not bond with anybody else. So our stable atoms are group 18. We are going to give them a name. They are called the noble gases. And the way I know that they are stable and they have a full energy level is because in the top right corner, it's a 0. A 0 means that they are not bonding with anybody. So if you look at helium, neon, argon, krypton, they have zeros up in that corner. So that's showing they're not forming ions. So how many valence electrons does it take for hydrogen and helium to be full, to be stable? So they only have one electron shell, and that first electron shell is full when it has 2. So it takes 2 to be stable for hydrogen and helium. But everybody else on the entire periodic table, I want you to look at the ending numbers. So everybody in group 1 going down, they all end in a 1. Everybody in group 2 ends in a 2. And we go over and we look at group 18. What does it mean to be full? They all end in the number 8. So the octet rule, I like to say 8 is great. Having 8 valences, 8 electrons in your valence shell is just perfect. So that is why it's called the octet rule. 8 valence electrons is full, and so full is stable. All right, atoms will form bonds, metallic bonds, ionic bonds, covalent bonds to complete the octet rule. So in a metal, atoms, what do? They constantly share and pass. Actually, I'm not going to use the word share because I want to save that word for covalent. So they constantly pass their electrons back and forth, creating a mobile sea of electrons. So think of like hot potato. None of these metals really want their electrons, so they're constantly passing them to the next metal atom, and so that's what creates this sea of electrons. All right, in an ionic bond, metals are transferring electrons to the nonmetals. And they're doing that to be stable. And nonmetals are going to gain, I sort of wrote it all in there. They are transferring electrons to the nonmetals, and the nonmetals gain the electrons from the metals. All right, the metals are losing the electrons, and so they are becoming positive ions. And the nonmetals, when they gain the electrons, they become negative ions. All right, together they form a stable ionic compound. All right, so now we go back to B2, 4, 5, 7, and 8. Use this information to complete the table. So again, I'm going to do the first one with you, and then you can do the rest. So potassium, number of valence electrons. So potassium just had 1 valence. Meets the octet rule as an atom? No. it doesn't. It doesn't have 8 in its outermost shell. Is it stable as an atom or is it likely to bond? It is likely to bond. Gains or loses electrons in an ionic bond, and how many? Okay, it is going to lose 1 electron. So now look at potassium. It was 2881. That was its electron configuration. I'm just going to write it over here, 2881. If it loses that 1, look, the next energy shell in, which is now going to be the outermost shell, it's full. It meets the octet rule. So that is what they figured out is like, hey, why are these atoms forming these bonds? And it's all about the electron. All right, Lewis dot diagrams. So you might think that drawing those atoms are fun to do until you're asked to draw something gigantic like francium. So francium has 7 energy levels. So luckily, this man Lewis, he had this creative, this easy way to show valence electrons. So they're the outermost, so they're the ones that we really care about. The inner electrons aren't as important in bonding. So we're going to do what are called Lewis dot diagrams, and they are going to only show valence electrons. So there's a specific way in which the valence electrons are distributed around the element symbol. So this is not an element right now. X is just my any element will do. Remember that 8 is great. The goal is to have 8. So there are 4 sides. There's one side here, one side here, one side here, and one side here. So there's 4 sides where I can show these 8 valence electrons. And so each side is broken into 2 spots. So this is my spot 1, and this is my spot 2. Then what happens is as you go around, you only fill 1 on each side next. So this and this are my spots on this side. I'm going to fill just this 1. Then down here at the bottom, I have these 2 spots. I'm going to fill just this 1 next. And on this side, I have 2 spots, and I'm going to fill just this 1 next. So I want to compare this to getting on a bus. The first 2 seats that fill up are the 2 bus. Okay, so imagine I'm getting on a bus. Here's the driver. You get on the bus. These are the 2 best spots, 1 and 2. So those get filled right away. Boom, boom. Everyone wants to sit in those spots. But after that, you go like, I'll take this one and leave this one open. And then I'll take this one, but leave this one open. And the next person's like, I'll take this one and leave this one open. So let's say those are all the seats on the bus. You'd rather sit by yourself than with somebody else if you didn't get one of those 2 best spots. So the 2 best spots are the 2 top ones. Those are what we're going to fill first. And then we're going to fill in our dots according to this plan. So the 3rd best spot, the 4th best spot, the 5th best spot. Then I keep going around. So I'm going this way around. And now if I'm electron number 6, I go in this spot. If I'm electron number 7, I go in this spot, and then the last spot is right here. So that 6th person getting on the bus would go here, the 7th, and the 8th. So that is the arrangement. Now, let me do a couple examples. So if you see, what the heck am I talking about? So let's pick an element. Let's pick, well, let's see, which one didn't I do later on? Let's do sulfur. So sulfur is 2-8-6. All I care about is the valence electrons. So there's 6 valence electrons. So there's 1, there's 2, there's 3, 4, 5, 6. Oh, I love drawing these. So nice to draw these versus all those rings and all those electrons. I have to put the 6 dots in those specific locations though. All right, let's say I have lithium. Lithium is 2-1. So there's only 1 valence, 1 dot. Boom, done. That's it. That's all I need to draw. Let's say I do iodine. Iodine is 2-2. 8-18-18-7. Okay, 7. Spot 1, spot 2, 3, 4, 5, 6, 7. The only one that's left open is that 8 spot over there. So think of each side as a little shelf to hold 2 electrons. 2 here, 2 here, 2 here, and 2 on this side. Okay, so let's do some practice. So potassium was 2-8-8-1. Circle the valence. Do the Lewis dot diagram. Done. Instead of drawing all those rings and all those electrons, I just do the 1 dot in the 1 dot spot. Okay, so go ahead, pause me, and go ahead and do these practice ones. All right, and then when you're done, come back. Okay, so now you're back. So now you're ready to do Lewis dot diagrams for ionic compounds. So when an ion forms, valence electrons are often complete. The whole idea is to become stable. So I'm going to show this to you in a few steps, and then I'm going to show you what the final answer will look like. So let's do MgO. All right, we'll start with that one. So MgO is a compound formed from magnesium and oxygen. Magnesium has 2 valence electrons, so it would have 2 dots. Oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. So I'm going to show you what actually happens. It's just like when you cut your little pieces. The electrons move from the metal to the nonmetal. So Mg is going to lose 2 electrons. So I'm going to draw it like this. Mg, I'm going to give it brackets, and I'm going to give it a +2. The brackets show me that the outermost shell is now full and that the charge is now a +2. It has lost 2 dots. So I don't show those 2 dots anymore because I've lost them. And I don't show the 8 that are under that. I like to show that it just has lost its outermost 2, meaning the next one in is going to be full. Oxygen needs all of its dots. So it only had 6. I need to show that now it actually has all 8. And so over here, I'm going to put brackets to show that it's full, and I'm going to show -2 because it gained 2. It used to be 6, and now it has 8. So that would be my Lewis dot diagram for MgO. So I like to say that ionic compound Lewis dot diagrams are as easy as A, B, C, D. A, write out the atoms. B, put brackets around them. Always distribute your atoms so the pluses and minuses are next to each other, and that 2 negatives or 2 positives aren't touching. All right, C, put the charges on. And D, put dots for electrons only on the negatives. All right, so let me do another one with you. Let's do a hard one. Let's do iron 3 oxide. All right, so the formula for iron 3 oxide, Fe is a +3, O is a -2. Crisscross, my formula would be Fe2O3. Okay, atoms. First thing I need are 2 irons and 3 oxygens. So 2 irons, 3 oxygens. Just like when you did your particle diagrams, separate out the atoms so that no atoms with the same charge, or now they're ions with the same charge, are next to each other. So that's my A. B, give everybody brackets. C, give everybody charges. O's were -2s. FEs are +3s. Make sure it adds up to 0. 3 and 3 is 6. -2, -2, -2 comes out to -6. So perfect. And then last thing are the dots. O now has all 8. So 2 on each side. And Fe has none because it lost its dots. So there it is. There is like the most complex Lewis dot diagram you could have, is something large like that with all of those charges. All right, let's move on. Next is some practice that you're going to do. So here you go. Do the practice and then check in with me and we will go over it. I'll continue the rest of this on the next video.